Now, please proceed.
Okay, I'm waiting for the message.
No, I think
No,
it is.
it is live. It is live.
It's live already? Oh, okay.
Yeah,
Great.
yeah.
Oh, so we can start then.
Okay. So good afternoon, everyone. Welcome to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly organized by South Asian Meteorological Association, SAMA, and Savitribai Phule Pune University, SPPU. Today's lecture will be delivered by Dr. Somenath Dutta sir, who is from IMD Kolkata. But before we proceed for the lecture, I would request Dr. Dheeraj Pradhanang, who is also the member, Executive Council, SAMA from Nepal, an associate professor, and also the head of the Department of Meteorology, Trichandra Campus, Tribhuvan University, Kathmandu, Nepal, to please deliver the welcome address.
Thank you, Dr. Rohini, Howard, for including me. Namaste and good afternoon, everyone. I'm very much, in fact, pleased to welcome all to this lecture number 16 of the weekly online lecture series on atmospheric dynamics and its application to climate sciences, which is being jointly organized by SAMA and SPPU, as Dr. Rohini mentioned. And today it's a special session. We are privileged to have Dr. Somenath Dutta from the India Meteorological Department, IMD, Kolkata, with us. This is a really great privilege to have you over here, Dr. Dutta. And he, as per the brochure we have, he will be speaking on a fascinating topic on equatorial wave theory, covering mixed Rossby gravity waves, Kelvin waves, and vertically propagating planetary waves. These are the areas which is not only theoretically rich, but also critically important in understanding tropical atmospheric dynamics and their broader climatic implications. In my context, I'm very much delighted to have these kind of science being discussed in this series. And understanding this kind of equatorial wave dynamics, which is not only crucial for improving forecasts of monsoon and extreme events in South Asia, but they are also very much important in assessing how they influence snow and glacier processes in the high mountains and their downstream impacts, which is the very much focus of this year's International Year of Glacial Preservation 2025, and also the UN Decade of Action for Cryospheric Sciences 2025 to 2034, when we are working for the sustainability of mountain with this changing climate. And I understood from the discussion that this platform brings scholars, students, early career professionals from South Asia and beyond 50 plus countries. That's amazing. And more than 1150 participants registered for live one as well as to watch the recorded one. So this is a really great platform, and I'm very much happy learning about this environment, especially promoting regional collaboration in meteorology and climate science. So once again, on behalf of SAMA and the organizing committee, I extend a very warm welcome to Dr. Dutta, all the participants watching online as well as live over here, and our partners from SPPU, Savitribai Phule Pune University, and let's look forward to an engaging and insightful session. And thank you once again. Back to Dr. Rohini Bauer. Thank you very much.
Thank you, sir. Thank you very much. Now, as our speaker we have already introduced in the last lecture, so I request Dr. Dutta to please share his screen. And
Yes.
I also request all the participants to please type your questions in the Q&A box, and the attendance link will be shared after 10 minutes.
Can you kindly...
Yes, we can see, sir.
So, good afternoon to everyone, my respected professors, Tagi sir, my senior DGIMD XT and my senior professor, Professor Das and others. So, so today we will discuss about the equatorial wave theory. Now equatorial wave theory, we will discuss some important wave, that is equatorial Rossby wave, equatorial inertia gravity wave, mixed Rossby gravity wave, and Kelvin wave. Now these equatorial waves are very important wave. Why we are calling it equator? Because these waves are equatorially trapped, as if equator is guiding these waves like this. That means magnetic gravity wave, mixed Rossby gravity wave, and that means a amplitude of such waves decays as one moves away from the equator. So now what happened for discussing these waves, one thing it is regard, because in every wave actually when we will discuss, we will find that one of the important force will be Coriolis force. This time Coriolis force will be there. So now near equator actually we will apply the beta plane approximation. Now regarding beta plane approximation, just I will tell you one thing, that you consider a very narrow latitudinal belt around one reference latitude. In this today's case, it is your equator, but it may be any latitude. At mid latitude, we take 45° north. You consider a very narrow latitudinal belt about a reference latitude. Okay, so now if you consider the entire belt, the surface of the belt will look like a curved surface. I hope everybody will agree. But if you consider a limited part of the belt, then that limited part will appear as a plane, and this plane we call it beta plane. And in this beta plane, it can be shown that the Coriolis parameter varies linearly with latitude, that means y. So we generally say like this, that Coriolis parameter at any latitude y is equal to Coriolis parameter at the reference latitude plus beta y. Y is nothing but the departure from that reference latitude. So now here actually in equatorial wave theory, we will apply the equatorial beta plane approximation. In case of equatorial beta plane approximation, the reference latitude is equator. And at the equator, value of the Coriolis parameter, we all know very well, this is equal to 0. So therefore, in our discussion, everywhere the Coriolis parameter will be approximated as f is equal to beta y. So this is known as equatorial beta plane approximation. So now to discuss about the equatorial wave theory, what we consider one incompressible fluid with variable lower boundary, because we know very well sea surface mean sea level pressure is not, our air is not same, terrain is not smooth, and it is a fixed upper boundary, say capital H, and this is the variable lower boundary. So now here actually we consider three governing equations. One is your U momentum equation, another one is your V momentum equation, another one is your continuity equation. So now this equation we all know very well. This equation looks like this. If frictionless flow, if I take, that is du dt is equal to, you can find that this is equal to minus g into del h del x plus fv. Fv means beta y into v, and then dv dt. This will get minus g into del H del Y, then minus beta Y into U, and continuity equation, it will look like this. It will be your G into H, G into H, del U del X plus del V del Y into plus dH dt is equal to 0. So these are the three governing equations. Now these three equations, as we apply, these three equations are linearized using the perturbation technique. And in the perturbation technique, we consider a motionless mean flow. Motionless mean flow. We consider a motionless, for simplicity only, motionless mean flow. So if I consider a motionless mean flow, so that means in that case, my u will be is equal to just 0 plus u prime. That is perturbation only, which is a function of x, y, t. Similarly, v will be also like this. This will be is equal to 0 plus v prime x, y, t, and this small h, this will be is equal to, that will be a mean height plus some perturbation. So now when you substitute, then the linearized equation, it will be like this actually. Then the linearized equation will be like this. Yeah, linearized equation, it will look like this. That is your del u prime del t. Okay, then is equal to minus del phi prime del x. This phi prime is nothing but g into small h prime. H prime is nothing but perturbation height. And then this will be is equal to beta into y into v prime. Then del v prime del t. For any wave equation, whatever may be the wave, to get the dispersion relation, the step is like this. First, to write down the governing equation under the assumptions taken. Then governing equations are linearized using the perturbation technique. Then the linearized governing equations are simplified to get only single perturbation equation. Then the perturbations are approximated to have a wave character. Then the wave formula is substituted, and then we get the dispersion. Here also we will do like this only. So we are now doing the second step. So this is your second equation. And then we will have our next equation is your continuity equation look like this, GH into del U prime. This equation you can remember, it is to some extent similar to our last class. We discussed shallow water gravity wave equation, that is our external gravity wave equation. Okay, and then this, then plus del phi prime del t, this is equal to 0. Okay, so second part is over. Second step is over. Next step is all this perturbation quantity, that is u prime, v prime, w prime, phi prime. This we are expressing like this. because perturbations are function of x, y, and t. Y dependence we are taking care in their amplitude. In their amplitude. Y dependence. We are considering the amplitude. And x and t dependence we are taking care in the simple harmonic type of motion. You can understand I kx minus nu t. Nu is the frequency, k is the wave number. That means we are considering the perturbations are having wave structure. What type of wave? Progressive wave. Minus nu t is the progressive with respect to time with frequency nu and wave number k, and with amplitude which is varying with y. How it is varying? Our assumption we have to remember this amplitude should be in such a way that amplitude should decay away from the equator. That means in mathematical sense that magnitude of all this amplitude should tends to 0 as y tends to plus minus infinity. Now when we substitute in all these equations, okay, and then after the simplification, lot of simplifications are there. I will request my participants, if possible, they can do this exercise. It is a very good exercise. Once you do first time, there will be some difficulties, but after that you will enjoy. After simplification, that means first we have to substitute all these equations, then you have to just simplification, algebraic simplification, then ultimately you will get one equation. Second order partial differential equation, del 2 v tilde del y2 then plus within bracket nu square divided by g into capital H minus k square minus k into beta divided by mu minus beta into y square divided by g into h v tilde, this is equal to 0. You can understand it is not a very simple equation because inside it is not a constant, it is a variable, y square is there. So now if we look the quantities in the bracket, it may be very small. If it may it may be very small now. The quantities in the bracket, this quantity, suppose if this quantity, if I call this is equal to omega square, let us say, then you can see very well that this omega square will be greater than 0 if this mod y is very small. This is very small. Very small. You can see very well. And in that case, we know very well what type of solution we will get. We will get a wave-like solution on the sine cosine simple harmonic motion. And but if this omega square is less than 0, when it will be less than 0, you can understand if this magnitude of y is large enough, then this omega square will be less than 0. And if the omega square is less than 0, we know very well we will get an exponential solution. Actually, we will get two independent solutions. One exponents, one is e to the power plus something, another one will be e to the power minus something. Now, in these two, one will decay, but another one will grow. But we don't want grow because these are all equatorially trapped waves. So we don't want, we want it should it should decay. It should decay. So therefore, therefore, actually, Matsuno in 1966, he has shown that, first of all, one thing is very, very clear. Everyone can see that from this equation, one solution is very much trivial. That is, V tilde is equal to 0. That is very, very, yes, because this is satisfied. This is known as trivial solution. But we are not interested for the trivial solution. We are interested for the non-trivial solution. So, Matsuno in 1966, he has shown that the necessary condition for this system to provide a non-trivial solution is given by, I am showing you now. Its condition is, just a minute. Condition is this one, that is under root here shown. That is, this should be under root GH divided by beta within bracket nu square divided by GH minus K square minus K by nu into beta is equal to 2n plus 1. If this condition is satisfied, then only we can get non-trivial solution satisfying the boundary condition. What are the boundary condition? That is, V tilde y tends to 0 if as y tends to plus minus infinity. That means as y becomes larger and larger, magnitude becomes smaller and smaller. This is the boundary condition. So for this satisfying this boundary condition, trivial existence of a non-trivial solution of this equation is this one. That is this one. This condition was given by Matsuno in 1966. I am not going to include the mathematical details and all this equation. Actually, it is an eigenvalue problem. Boundary value, it is an eigenvalue problem. So from that, they have shown it. So now, question is that now what happened? That if n is equal to here, if n is equal to 1, 2, 3, that means all positive integer, then what? Then it resembles to, then what type of wave it gives? It gives gravity inertia waves. It gives gravity inertia wave. We call it inertia gravity waves. Gravity inertia wave. Gravity inertia wave. Actually, in case of pure gravity, internal gravity wave, we have seen already in the last class, pure internal gravity wave. There was, which forces were there? Pressure gradient force was there, and another one was the buoyancy force is there. But when we consider a gravity inertia wave, then that time pressure gradient force of course will be there, buoyancy force will be also there. At the same time, Coriolis force will be also there. Gravity inertia wave. Then n is equal to 1 to 3. It also gives Rossby waves. Rossby wave. And for n is equal to 0, it is a special type of, we call it mixed Rossby gravity wave. We will discuss in details mixed Rossby, popularly known as MRG wave, Yanai wave also. Mixed Rossby gravity wave. And for n is equal to minus 1, n is equal to minus, if it n is equal to minus 1, then it is Kelvin wave. So one by one, we will see now. So actually, what happened, you know, this is the dispersion relation. It is nothing but the dispersion relation. Now, if you see this dispersion relation, we can find this is nothing but a cubic equation, isn't it? It is a cubic equation. Cubic equation, I can write down, just a minute. It is just a cubic equation only. Just a minute. Yeah, we will. It is just a cubic equation which looks like this. Nu cube minus, it is a complicated type, of course, minus, everyone can check, it will be like this only, gh k square plus beta into 2n plus 1 within bracket root gh minus beta into k into g into h, this into nu minus, I'm sorry, beta will be, just a minute. Here will be nu and then minus beta into k into g into h. This is equal to 0. It is a cubic equation. And now from the basic law of polynomial equation, we can see that this equation give, first of all, this equation must give three roots of nu. So, and by analyzing the different equation roots, relationship of the roots, we can see that this equation will give rise to one negative root and two positive root, or two positive root and one negative root, like this actually. As such, it gives rise to westward propagating wave and eastward propagating wave, both. Okay, westward propagating wave and eastward propagating wave. Okay, so westward, we will get westward and eastward propagating your gravity wave we will get, and we will also get your equatorial Rossby wave, which is your westward propagating. We call it easterly wave. Okay, so now there are some special case we can now discuss. That's some special case. That special case number one, that suppose that if the top of the atmosphere, it is at infinity, that means if h tends to infinity, then what happens? Now here itself we can see if h tends to infinity, where is that equation? Sorry, if h tends to infinity, then what will happen? Then this term will go, this term also will go, then we will be remaining with these two terms only, isn't it? So then how the equation will look like? So it will look like del 2 nu, del 2 v tilde, sorry, del y2, then minus into k square plus k beta by nu, k square plus k beta by nu, k square plus beta into k by nu, into v tilde. This is equal to 0. Now, if I seek for a wave-like solution of this equation, that means v tilde is proportional to, say, e to the power I into L into Y. If I put, then what you will get? You will get, you can see very well, that is minus L square minus K square minus beta Ky nu. And from here, you can see that you are getting nu is equal to beta K divided by L square plus K square. You remember in the last class we discussed, we got this expression for the Rossby wave. What am I point? So therefore, so Rossby wave dynamics, it is remaining same in the equator, in the near equator also. Now special case, so it is nothing but the Rossby wave only when as h tends to infinity. Then special case 2, special case 2, when we don't consider the rotation, we don't consider the rotation. That means suppose if beta is equal to 0, if we don't consider, then in that case, how this equation will look? Beta is equal to 0 means this term will 0, this term will be also equal to 0. So will be remaining only this two term. Okay, fine. So then we will have this one, that is del 2 v tilde del y2, then plus nu square by gh minus k square, sorry, nu square by gh minus k square, nu square by gh minus k square into v tilde, yeah, square nu square gh minus k square v tilde is equal to 0. Again here, if I consider this type of solution only, then again you will, what you will get, we will get minus L square plus nu square by gh minus k square is equal to 0. And you can see, we can see that here we will get this relation, that is nu square is equal to gh into k square plus L square, k square plus L square. So this is nothing but nu is equal to under root gh into under root k square. Let us remember that in the last class when we discussed about the external gravity wave, only thing is here L has come because here we are considering motion in the horizontal plane along x and y both directions. That's why L has come. It is same as the gravity wave, that is external gravity. Now we will consider the general thing. The general thing already we are discussing, that it is basically a cubic equation in the frequency which gives rise to positive negative root, and it gives rise to inertia, that is your eastward and westward propagating gravity wave, equatorially trapped, and another one is your westward propagating equatorial Rossby wave, which is very famously, we know, synoptician, we call it easterly wave. It is very, very important wave, this easterly wave. Many times this easterly wave near equator, when it interacts with upper level of high latitude Rossby wave, then in juxtaposition and in a favorable orientation, it gives rise to very good rainfall, very good weather activity over tropics. And not only that, we also know that that equatorial Rossby wave plays a very important role by providing vorticity, initial vorticity with available tropical convection for the genesis of the storm and all these things. Okay, so now we will discuss the special case, that is when n is equal to 0. When n is equal to 0. So when n is equal to 0, then what happened? Then we'll see, then our dispersion relation, it will look like this, that is gh under root beta and then within bracket nu square by gh, nu square by gh, nu square by gh minus k square, minus k square, and minus k nu by beta, nu by beta, k nu by beta. This is equal, n is equal to 0 means this is equal to 1. So therefore, this equation can be simplified as, this equation can be simplified as like this. Yeah, it will be your nu square by gh minus k square minus k by nu into beta, then minus beta divided by under root gh. This is equal to 0. So let us simplify it. If I simplify it, then it will be like this. That is your nu cube minus g into h into k square, then plus beta into under root gh, into nu minus beta into small k into g h is equal to 0. We will get, and we can factorize. If I factorize, we will get two factor. One is your nu gh under root gh minus plus k, and another one is your nu under root gh minus k minus beta by nu. This is equal to 0. So now it gives two situations. One is this one, another one is this one. This one is not allowed because I have not shown you the entire derivation, because if this one you make it 0, then what happened? It will contradict our own hypothesis itself. So this cannot be equal to 0. So therefore, our dispersion relation is this one. Which one? That is your nu divided by gh. Sorry. That is nu divided by gh under root, of course, minus k and minus beta by nu. This is equal to 0. So it is a quadratic equation. We can see very well. And by solving this quadratic equation, we will get this relation k nu is equal to k under root g h, then within bracket half, then plus minus again half, then within bracket within square root 1 plus, it is a complicated relation, 4 beta divided by k square into under root g h. So from here we can see, you will get that for positive one, you will get, for negative also you will get. Positive root corresponds to that positive, nu positive, the positive, it corresponds to equatorially trapped westerly inertia gravity wave. Equatorially trapped westerly, equatorially trapped, trapped westerly gravity wave. Westerly, basically it is inertia gravity wave, inertia gravity wave, and mu negative, actually it corresponds to two things. One is your easterly gravity wave, and also easterly gravity wave, and also your equatorial Rossby wave, equatorial Rossby wave. Equatorial wave, that when the periodicity of the wave is about synoptic scale, actually when we consider the synoptic scale wave, then it will resemble to our equatorial Rossby wave. So these are about your mixed Rossby. That's why this case that is n is equal to 0, it is called the mixed Rossby gravity wave, because this n is equal to 0, this mode gives rise to gravity wave also and Rossby wave also. So that's why it is known as equatorial Rossby. Now we will consider the Kelvin wave. Okay, equatorial Kelvin wave. For Kelvin wave, we will have those same equation only. Only thing is we should not have any V. There is no V as such. There is no V. Okay. So from this we should start from this actually. So when I consider the Kelvin wave, then this should not be there. When I consider the Kelvin wave, then this also should not be there. This also should not be there. Okay, because it is along the equator only, no meridional perturbations, So therefore, and on this equation, we will apply the same thing. Only thing is this will not be there. Of course, this will not be there. We'll apply all these things, and then ultimately we'll get what? We'll see now. We'll see that ultimately we will get these three sets of equation. One equation we will get this one, that is your one equation we will get your minus I into nu into u tilde plus I into k into phi tilde. As I told you that phi prime is equal to g into h prime. So phi tilde, that is nothing but Fourier transform, that is g into h tilde. This is equal to 0. So from here you can find, you can get u prime in terms of phi prime or whatever you want. So we can get u prime in terms of phi prime, of course, that is k phi prime divided by nu, you will get. And then another one equation also which is there, that is your minus I nu phi tilde plus g into h into ik into u tilde. This is equal to 0. So from these two equations, if I eliminate, then you will get this dispersion relation, that is nu square minus GH K square is equal to 0. So from this is the dispersion relationship for the Kelvin wave. And accordingly we'll get nu is equal to, suppose it may be plus minus K into GH. So therefore phase velocity C, phase velocity, this is equal to nu by K. This will be is equal to plus minus under root GH, and of course this will be is equal to group velocity also, that is CG, which is equal to del nu del K. So therefore one thing we get that Kelvin wave is a non-dispersive wave. So now question is, this plus minus both are there. Now we are having another one equation actually. So that equation is your del phi tilde del y plus beta into y divided by c. This is equal to 0. So now if I integrate this equation, then you can see this equation, it will be like this: phi tilde y, this will be is equal to phi tilde 0 into e to the power minus beta y square by 2c. So here actually this equation is very much helpful to decide whether c should be positive or negative. So now for the sake of argument, even if I take c is negative, then in that case what will happen? This entire portion, this will be positive, okay, with y square multiplication. Then in that case, if y tends to plus minus infinity, that means if one goes away from the equator, then what we are finding, the amplitude is not decreasing, amplitude is increasing. Okay, so this is contradicting with our hypothesis. So that's why we should not take c negative. So therefore c should be positive. C should be positive. So therefore for Kelvin wave, c is equal to, now definitely c is equal to plus under root g into h. So that's why Kelvin wave is eastward propagating wave, that is westerly wave. Kelvin wave is eastward propagating. So with this actually equatorial wave we have finished now. So actually in that last class, I remember one thing I was just discussing, but I could not that in case of Rossby wave, you have seen that c is equal to u bar minus beta by k square. If I remember, beta by k square, where k is equal to 2 pi by L. L is the wave number. So now I may be curious to see that for which wavelength of Rossby wave this c will be exactly equal to 0. That means stationary. Rossby will be stationary. That means stationary. No wave, no speed, phase speed. Okay. So this is very simple. You can put it here. If you put it here, then you may find out that L is equal to, you may find out L is equal to 2 pi under root L, U bar divided by beta. That means you first of all, you choose one latitudinal belt. So for that latitudinal belt, you have some beta, you can find out. And in that latitudinal belt, what is the mean zonal mean, you can find out. And accordingly, we can find out what is the wavelength of that particular Rossby wave group existing over this latitudinal belt with this mean wind, so that Rossby wave is stationary. Okay, it is not moving, and this is known as critical Rossby wavelength. Yesterday, last class I was discussing, no, L is equal to LC. Now, as an exercise, I will request all the participants that you can just try that in this relation. Once you put L greater than LC, and then you see what sign of C you are getting. I am giving you the answer, you will get C less than 0. And another one case you do, L is less than LC, you will get C positive. That means you are getting one thing, that long, very long Rossby waves, they are retrogressive, and shorter Rossby wave, they are progressive. Actually, experimentally, observationally, it is seen that if Rossby waves with wavelengths of the order of 10,000 kilometers like that, they are in general retrogressive. And Rossby waves with wavelength 3,000, 4,000 kilometers like that, actually, they are your what is called progressive. So with this, today I will stop now.
Okay, sir. Before we go for the question answer session, I would request all the panelists to switch on their cameras. We will have a photo.
Just a minute. Huh?
Yes, sir. Meanwhile, I also request the participants to please write your questions in the question answer box. So can you unshare the screen?
Oh, acha. Just a minute. Okay. Just a minute. Stop.
Yes.
Now I have, it has answered.
Yes, sir. Yes. Ashwin, I request to take a picture. Okay. So now I request Ashwin Jadhav, who is from SPPU, to please conduct the question answer session.
Just one thing. If I get an opportunity sometime, I think I will be able to save some time in my further classes, the 15-20, that time now, I will discuss about this vertical propagation of stratospheric equatorial wave. Equatorial wave, when I will consider the vertical propagation, then set of equations will be little bit different. Okay, that I will discuss sometimes later. I hope that I will be definitely able to get some time. I will be able to save some time in my forthcoming lecture. I will do that. Thank you.
Sure. Yes, sir.
Sure, we shall provide you, if possible, one more lecture at the end.
If possible, it is fine. Otherwise, I will try to manage.
We'll see.
Thank you, sir. Thank you for a wonderful lecture. So there are two questions from the same person, Johnson. First is whether these waves found in atmosphere or ocean or in both.
Both.
Okay, sir. Okay. And second question is, these waves considered as ocean-air interaction?
Yes, that's why they are so important. As such, I am telling you, they are basically one of the, as you know, in extratropical latitude, we have a very nice thing is there. That is your index cycle, Jonah index cycle. That's why extratropical people, just like Hero Mastan, they used to say, our forecast are always correct. Our forecast are always correct. Because they have a very nice pattern, but we don't have. They are once index cycle set, everybody knows. After 7 days, after 10 days, what will. But in our tropical latitude, it is not there actually. So there are many drivers. One of the drivers are equatorially trapped these waves. It is a very, very important. Even I remember when I was just a mid-grade 2, Dassa, I remember that time, you know, our R.N. Kesomurthy sir was there.
Yeah.
IITM director. I was just asked, just said this Enso, yes, it is moist Kelvin wave. He told that immediately, told moist Kelvin wave. It is so important actually. Even I am telling you, I have a very little knowledge about equatorial waves only. You will find a lot of experts who are really very, very experts in equatorial wave. So for equatorial wave itself, they can have a course, 3 months, 4 months course as such. It is so vast, so important. And it is tricky also to some. You can see, if I have skipped many things. Had I continued, Hermite, polynomial, all these things, many people might be I might be inviting many people to sleep as such, although they are very nice equation and all these things. You can see that Gill paper and all these things, Randall Gill, all these things, very nice analyses are there. So this is just an introduction, just a flavor as such. If you like this flavor, then you can run after the big vendors to get this food, better quality food. Whatever I have providing, it is just like a street food actually, street food flavor. And if you like this flavor, you go to mall, you go to good restaurant, and you fulfill your desire actually. Thank you very much.
Thank you, sir. Thank you so much. As of now, there are only third question is there from Priya Kumari. So, how atmospheric Rossby waves interact with monsoon dynamics?
Actually, what happened, atmospheric Rossby, I am understanding she must be referring that equatorially trapped Rossby wave only. So now we know very well, whenever there is any wave is there, wave is there, that wave, that at some part of the wave there is cyclonic vorticity maxima, at some part of the wave cyclonic vorticity is minima, that we know very well. So now equatorial Rossby wave, while propagation, if the maximum cyclonic vorticity zone coincides with the convectively generated heating place there, then definitely you can understand that initial vortex provided, heating is also there, it will be genesis of the system will be there. And not only that, during monsoon season also, when some bad monsoon to good monsoon phase is there, that time also equatorial Rossby wave plays very important role. And extratropical mid-latitude Rossby wave, the big roles are there. Mid-latitude Rossby wave, very simply, let us call it westerly wave only. Let us call it very simple thing, mid-latitude westerly. Now, during southwest monsoon season, if the westerly wave position is such a place so that there is very strong cold northerly advection is taking place over our northwest region, you can understand, I need not to tell what will happen. Our monsoon current will be weaker. So Rossby wave has many things to interact with, not only monsoon and any types of tropical atmosphere, actually tropical weather phenomena. I hope I have been able to clarify.
Yes, sir. Next question is from Priyanka. Does the equatorial Rossby waves can interact with the mid-latitude Rossby waves? And when the mid-latitude Rossby wave penetrates southward?
Yes, at that time itself, very correct. Can I share the screen?
Yes,
Yeah.
yes.
Sure, sir.
Just a minute. Let us take, suppose this is your upper air mid-latitude Rossby waves. Penetrating, penetrating, let it be penetrating. Okay. Trough, ridge, is upper air, mid-latitude and lower level. So now what happened, over this region, there is upper level divergence is there. Okay, upper level divergence is there. And I could not draw it properly as such. Just a minute. Suppose orientation is like this. As such, dynamic meteorology must be integrated with synoptic meteorology. Otherwise, it is just like that. Marriage should always be with a male and female only, like that actually. So dynamic meteorology alone is not sufficient without synoptic meteorology. This is the trough in the low level. Now what happened here? at the low level, there will be convergence. There will be convergence. And here at the upper level, there is your divergence. So for this divergence, it will suck. It will suck. And for this convergence, it will push. It will push. As a result of which, over this region, there will be strong rising motion, strong upward motion. And due to moisture convergence, lot of cloudy weather phenomena. I hope I have been able to.
Yeah,
Yes,
quite
sir, yeah.
interesting, certainly.
Yes, sir. Thank you so much, sir. Thank you.
Yeah, in fact, the lower one is the
So
easterly
there
wave,
are,
the upper one is the westerly wave. So,
Yeah, please. Any other questions, sir?
so there are no more questions. So we encourage participants, if they have any more questions, they can
Yes,
email
more question.
anytime to Somenath sir, or they can email us.
Yes, yes.
Thank you. Thank you
sir.
so much.
Yeah,
Thank
thank you, sir. Thank you,
Thank you.
Ashwin.
Thank you.
So now I request Dr. Mili Ghosh Nilala from BIT Mesra to please give vote of thanks. Ma'am, I will share the screen.
Yeah. Thank you, ma'am. On behalf of the organizing committee, I express my thanks to each one of you for your contribution for this 16th lecture of weekly online lecture series on atmospheric dynamics and its applications to climate sciences. Firstly, I would like to thank Dr. Dheeraj Pradhanang, Member Executive Council, SAMA, Nepal, and Associate Professor, Department of Meteorology, Trichandra Campus, Tribhuvan University, Kathmandu, Nepal, for giving welcome address and brief information about this lecture. My deepest appreciation goes to our speaker of the day, Dr. Somenath Dutta, Senior Scientist G, IMD Kolkata, for delivering consecutive second lecture and very informative lecture on equatorial wave theory, mixed Rossby gravity waves, Kelvin waves, and vertically propagating planetary waves. I also thanks to Mr. Ashwin Jadhav from SPPU Pune for nice conduction of question and answer session. My sincere thanks goes to Dr. Rohini Bhavar from SPPU, the program convener, for moderating today's session. I express my heartfelt thanks to all the panelists and participants who joined us from across the globe. Last but not the least, I want to thank team members of Savitribai Phule University for their support in organization of this lecture. Thanks a lot. Thanks a lot, sir, for a wonderful lecture.
Thank you, Dr. Nilala. So now I request, yes,
Rohini,
yes, sir.
yeah, let me emphasize the aspect that yes, we have to link dynamics with the synoptic meteorology. And the purpose of this lecture series is the application of atmospheric dynamics in weather and climate. So this is very important. It's not just a theoretical aspect of dynamics, it is about practical application, about understanding the weather systems and its forecasting. So this is request all participants to keep in mind. They should try to relate whatever is being covered in this lecture series with the synoptic and actual weather conditions. So that will be real application of it. Thank you.
Sir, yes, very important point you mentioned. Yes. So,
in fact, some of you might be aware that also we had some small discussion in our WhatsApp group. Datta साहब आप WhatsApp group में है क्या हमारा समा वाला? Probably नहीं है. Maybe you could join because we shared the link to all the members by email long ago. But no problem, I can send you the link once again. What I was saying is recently there was a discussion about the Rossby waves on the WhatsApp group. And some of you may be aware that the famous heat waves that occurred in Russia in 2010 and also the extremely heavy flood that occurred in Pakistan back a few years ago. They were all the result of the standing Rossby waves in some way because there was blocking high over Russia, and that caused a lot of heat waves. And also similarly, there was a stationary low for a long time over Pakistan, Afghanistan region that caused a lot of precipitation and rainfall, causing a lot of floods. These are all the practical aspects or practical implications of the Rossby
Correct.
waves.
Correct.
And certainly, it is very, very interesting, very, very important.
Because that what you are telling us, sir, I remember that is blocking high as such. When this Rossby or mid-latitude Rossby wave too much southern penetrating, blocking high takes place, omega type actually, and
Yes,
at the same time cut off low.
Yes, yes.
This actually.
Exactly. Yeah,
this is to blocking high, and this streamline goes like this actually.
Right. Yes. So very interesting.
It has a very actually, sir, this wave, these equatorial waves or mid-latitude waves, it is not only theoretical thing. It has a great practical. Practical means weather and climate. Have great practical aspects. In many places, as you have very rightly, in many places, climates are determined by such standing waves itself. Ours, and sometimes actually what happens, this type of waves are getting excited by some large scale mountain also. That is Andes जो है ना, Andes अमेरिका में ये Andes जो है हमारा Himalaya that time actually mountain waves.
That's right.
Mountain waves, short scale mountain actually vertically propagating mountain wave दे देता है, that is internal gravity wave. They are vertically propagating. So a lot of Pikeda study is also there, na? 1964 Pikeda study is there.
Yes.
Waves to the lee of circular mountain. He has proved using the small VA that Western Himalaya में वो जो आपका standing जो ये रहता है, trap जो रहता है, it is due to there is a mountain and western interaction. Theoretical study, लेकिन इसको ये 1964 it was, I think that time he was DG, still he wrote paper.
Yes.
Sole author paper. It's not only paper, sole author paper.
Right,
And I think it was a Monson Award also, 1964. Waves to the lee of a circular mountain.
That's right, yeah. I mean, if we have some time, if I can share my screen, I will show you the...
Sir, 1 minute. I just will tell the statistics there.
Oh, yeah, sure.
Okay, so 104 participants have recorded their attendance, and in that 88 participants have rated the presentation as excellent or very good. So,
very good.
Yes, sir.
Yeah, I was just saying that I can just show you a small clip of 1 or 2 minutes about the Rossby waves. If time permits, can I share my screen, Dr. Moin?
Yes, sir. Yes.
Okay, just a minute. Are you able to see my screen?
अभी तक आया नहीं तो.
Coming up?
Yes. Lee waves associated with a large circular mountain. Yes, Mohan Kumar Das, right. 64.
Yes, sir. Long back.
मेरा जन्म का 1 साल पहले.
Yeah, here it is.
You remember properly, sir.
And the Russian heat wave in 2010.
Because while doing my PhD work, I had read all these papers.
The number of such extremes has greatly increased. Part of this increase can be explained by simple thermodynamic.
Can you watch? Can you hear the voice?
Yeah, it is coming.
Assalamu alaikum wa rahmatullahi wa barakatuh, my dear brothers and sisters. Then
something is.
Innocent people of Palestine are in desperate need. They need our.
Something I think is overlapping this video.
Yes, Rossby waves and extreme weather.
Yeah, anyway, I think there is some problem because there is a overlapping video of advertisement here, which I don't know how.
Even sir, winter season में such standing ऐसा wave ना वो ठंडी का भी बहुत बड़ा देता है ना winter season में suppose if it doesn't move, that fellow Rossby wave doesn't move,
हाँ, yeah,
then जो एरिया में सोचिए आपका कोल्ड नॉर्दर्ली एडवेक्शन वो तो कंटिन्यू करेगा ना, तो
Yes,
उधर
yes.
आपका ठंडी बढ़ जाएगा.
Correct, yeah.
हाँ.
A lot of applications are there. So anyway, I think I will stop this because something is interfering this video.
हाँ, yes, अभी देख रहा है था कुछ.
So let me stop sharing my screen.
So should
Okay,
we
very good.
stop live streaming?
Yeah,
Then
yeah.